Okay, so 2.15 is a Gauss's law problem. Um, I boxed here Gauss's law. Now I'm just gonna go over the problem again. This will be the third time I recorded it, and both times my microphone did not work, and I just cannot be bothered to rewrite it a third time. So I'm just gonna walk you through what I have already written. Okay. Now I remember what Gauss's law is actually trying to do. Gauss's law is attempting to try and find the electric field at different regions, but only with perfect symmetry. So in this case, what we have is a shell. Okay, so the shell here, which I've marked in blue, has charge distributed on the inside of it, but it's sort of variable distribution, right? So there's more of them near the center and less of them as you work out. Now, there's three regions that we need to find the electric field in: before the sphere, or before the shell, I should say, inside the shell, and outside the shell. Now, the easiest one to do would be inside of the whole thing in here. So what you're going to do, and I'll erase to kind of show you. So inside, you need to pick a point. Man, you need to pick a point and then draw a Gaussian sphere at that point, and its radius we will call r. So when we write out Gauss's law, we say the integral, the closed loop integral of EdA is equal to the charge that's enclosed within that Gaussian circle that we drew divided by the constant epsilon naught. Now in this case, or I should say in most cases, you should always check to see if your charge enclosed is 0, because sometimes it will be, and that makes the problem very easy. So if we come back to our problem and we ask ourselves, okay, how much charge is enclosed within this Gaussian sphere? Answer, 0. There's no charges in there. All of them are out over here. So if the charge enclosed is 0, bam, that must mean that the electric field is also 0. All right, so let's move to the more difficult ones. So now let's move inside the shell. So if we move inside the shell, again, we're going to draw our Gaussian sphere. I just chose to draw it right here. But again, it makes no difference where you draw it. It's just to help you. So you draw your Gaussian sphere right here. It has a radius r, okay? And we're going to apply Gauss's law. The left side of Gauss's law. Well, the left side of Gauss's law is pretty straightforward, because the left side is this EdA side. And because of symmetry, this Gaussian sphere, Gaussian circle that I drew, should have the same electric field at all points, because they are all equally far away from the center. So what that lets me do then is I can just rip that E out of the integral. So all we're left with then is E, constant, times the integral of EdA. Well, just times the integral of dA. Well, the integral of dA is just A. So you're left with, on the left side, E times the area. Well, E times 4 pi r squared, the area of a circle. Or I should say the area of a sphere, the surface area of a sphere. All right, that's the left side of Gauss's law done. Now the right side. This is where it gets a little tricky. It's this right here, this Q enclosed. Now the reason why it's tricky is because the enclosed amount of charge, as you can probably imagine, will depend on how far you have drawn your Gaussian circle, right? If you've drawn your Gaussian circle very close to this inner radius A, not going to have very much charge. If you've drawn your Gaussian circle very close to this outer radius B, it's going to have most of the charge. So we have to come up with an integral to describe the total amount of charge. Well, the piece of information they give us is this rho. They tell us this rho is equal to k over r squared. Now, what's useful to remember is that rho itself has a definition. Rho is equal to the amount of charge per volume. Or, written another way, the charge is going to be equal to rho times the volume. Now, the reason why that's useful for us is because when we write out, in fact, I will erase this part and redo it with you so you can see. When we look at Gauss's, the right side of Gauss's law, we say Q enclosed over epsilon naught, but Q enclosed is going to be rho times dV. row, this row times the volume. Now, you might ask, well, why did I use dV? Well, that's because we're not talking about the total volume. We're only talking about the volume enclosed by this Gaussian circle. So I'm going to label that as dV. And then we still have our epsilon naught over here. Well, I can rewrite this because I know that rho is equal to k over r squared. And then we still have that dV. Now, we need to just take the integral. But there's one more trick. This dV can be rewritten as 4 pi. Well, let me actually rewrite it. That dV can be written as a dr. Because remember, all you're really doing to get to a volume is you are integrating the area. So what I can rewrite this as, instead of dV, I can rewrite this as 4 pi r squared dr, the area times dr. So that lets me rewrite this as k over, I'll put the epsilon naught first, epsilon naught r squared. And instead of dV, I'm going to put 4 pi r squared dr. Now we can take the integral, because I want to figure out just in terms of r. So now we have to think about what our limits of integration are. Well, the limits of integration are going to be from wherever the charges start, a, radius a, to wherever we drew our Gaussian surface. So our limits of integration would be from a to r. If you want to call it r prime or whatever, it's fine, or capital R. But that's just the radius that we've decided to have our Gaussian circle. All right, notice that this r squared and this r squared cancel. So our integral just becomes, and we can take our constants out. So we have k, oh, we have more than that. We have our 4 pi k over epsilon naught. Those are all constants. And then we have from a to r dr. Well, that's an easy integral. So we have 4 pi k over epsilon naught. So the integral of dr is just r, and it's going to be from a to b. Oops, not b, a to r. Plugging in our limits, we get 4 pi k over epsilon naught times r minus a. Okay, great. We have now finished both the left side and the right side of Gauss's law, so now we can just set them equal to each other. This side is our right side of the equation. This here is our left side of the equation. Set them equal to each other. So you have E times 4 pi r squared, that's our left side, is equal to 4 pi k over epsilon naught times r minus a. Now just solve for E. Notice the 4 pi's cancel. Bring that r squared over to the other side, and you're left with E is equal to k over epsilon naught r squared times r minus a. That is the equation for the electric field inside of the shell. Okay, now the last region is outside of the entire shell. The process is identical. You write out Gauss's law, Q enclosed over epsilon naught. The left side of Gauss's law is identical. There's no change, which is nice. The right side, though, the only difference this time is our limits of integration. Instead of going from A to R, we just need to stop at B, because once you've reached B, right, like once, if I draw my Gaussian sphere way out here, the charge is only enclosed between here A and here B. There's no reason to go from A to R, because including the R doesn't actually do anything, because there's no charges out here. It's only in this inner region. So our limits of integration then go from A to B. Well, you can see and go through the work yourself, but you'll end up with almost identical solution. The only difference is that instead of having R there, it's just B. So when you set those two sides equal to each other, the left side, which was the same, and the right side, which is just slightly different with this B, you'll get this as your answer for the electric field. Notice, again, it's identical to what we had before, except for this R now is a B. And that's it. You found the electric field in all three regions. Now, what it asks you to do at the end of it is to graph or plot the electric field as a function of R. Well, there's three distinct regions, right? There was inside the shell, or I should say on the inside of the radius A of the shell, in between A and B, so inside the shell itself, or outside of the shell overall. So all we have to do is just look at the equations we have for each of the three and graph them. So in region 1, the electric field was 0. Easy enough. But once we hit A, because this right here would be radius A, what does our electric field equation look like? Well, it looks like this. You can clearly see that as you increase your R value, your electric field is changing. How does it change? Well, it's sort of like this slow increasing parabola. But notice that it's starting to flatten out, which should make sense, right? It's reaching some maximum value. Once you reach this, which is B. Well, once you hit B, how does our electric field change? Well, once again, look at your equation 3. And now notice that as your R increases, you're no longer gaining electric field. You're actually losing it, right? Because now this is just a 1 over R squared graph because there's no R in this numerator anymore. So 1 over R squared. And what does that look like? It just looks like this. So this is sort of a general plot of what the electric field would be doing on the inside of the shell, in the middle of the shell, and outside of the shell.